Welcome everyone, my name is Corey Klinkhamer, a PhD student from the University of Windsor in Windsor, Ontario, Canada. I am presenting on our work entitled Modeling of Liquid Jet Impingement Heat Transfer on a Rotating Disk, Moving Reference Frame versus Moving Mesh. I am presenting our work on the behalf of our research group, which consists of Dr. Etemadi, Dr. Bella Chander, Dr. Barron from the University of Windsor, as well as Dr. Iyer from Magna International in Troy, Michigan, USA. Here is a brief outline of what we will be covering throughout the presentation, beginning with a very brief introduction, followed by a literature review. Then I will go into the computational methodology that was adapted for this work, and then I will go into some results and discussions that we have obtained. I will then end the presentation with my final conclusions. For many years now, researchers have been looking at jet impingement quite extensively for decades now. This is particularly due to their high convective heat transfer coefficients that we can actually obtain with jet impingement. Jets are becoming quite favorable for applications such as turbine blade cooling, power electronics cooling, as well as electric motor cooling. Last year, I presented on a jet impingement heatsink design for power electronics cooling, and now our research group is taking the exact same or a very, very similar concept, and we are now applying it towards electric motor cooling. For some typical electric machine designs, a cooling system may include a water jacket, such as what we see in the image below. The water jacket's main purpose is to remove heat that is generated within the stator windings. However, to cool the rotor, a more complex design may be needed, and this is where jet impingement comes into play. So the jets are going to impinge directly onto the rotor windings, which are rotating. Therefore, we have jets that are acting within a rotational field. Due to these jets acting within this rotational field, there is a large amount of complexity that is involved here, especially when you want to model the turbulent nature of the jets within this field. During the design stages of such a machine and such a cooling system, we can look at three main techniques, such as experiments, which are often expensive in terms of time and cost. We can look at lumped thermal networks, which are quite simple and however, they tend to suffer in terms of model accuracy. We can then look at computational fluid dynamics, or CFD, which is more computationally expensive than the lumped thermal networks. However, we do have an improvement in accuracy compared to them, and they are not as costly or time-consuming as some experiments may be. However, such a CFD simulation may be far too complex, and there are some solutions that typical researchers usually adapt in terms of modeling rotational fields. This may include moving reference frames or moving meshes. This brings me to the objectives of our current research. We are to investigate the heat transfer characteristics of an axisymmetric liquid impinging jet, which is impinging on a rotating heated surface. We are then to compare a steady moving reference frame approach to an unsteady moving mesh solution. Let's first understand the differences between the MRF and the MM approaches. We can see an image below here where we see a centrifugal pump with regions 1 and regions 2 defined with an interface between each region. For both the moving reference frame and the moving mesh approaches, region 1 is considered as stationary. However, for the moving reference frame, the cell vertices of the mesh for region 2 are stationary. However, for moving mesh, the cell vertices of the mesh for region 2 are actually rotating. Some distinct differences between the two approaches are such as for moving reference frame, we have lower computational cost compared to that for moving mesh. For moving reference frame, we can often implement steady state simulations, whereas a transient simulation is required for a moving mesh approach. Moreover, for moving reference frames, the domain that we are solving the solution on should be axisymmetric or very close to being axisymmetric. However, for moving mesh, the domain does not have to be axisymmetric and it can be fairly asymmetric. And we will discuss this later on in the presentation as well. The final point I want to make here is that for moving reference frame, we do have a reduced model accuracy compared to that of the moving mesh. I will now introduce the main parameters of interest here that impact the flow field and hence the heat transfer characteristics of the impinging jet on the rotating disk. First, there is the jet Reynolds number, which is deduced at conditions at the nozzle exit. Therefore, density and viscosity are determined at the jet temperature at the exit, and U is the average velocity at the nozzle exit. The length scale here is the nozzle diameter D, and the jet Reynolds number is within the range of 750 to 1500. Next, there is the rotational Reynolds number, which is based on the disk diameter D and the disk angular velocity omega. The Prandtl number is another important parameter, which is around 7 for water here in this study. I want to make a note here that the rotational Reynolds number is kept constant throughout the study and is constant at 3700. To determine the heat transfer performance, we are interested in the Nusselt number shown here, which is NUD. And this is based on the nozzle diameter D. To compare with existing literature, an average Nusselt number, NU bar, is going to be computed and compared with the works of Karper et al., and this will be shown later on in the presentation as well. The literature spans multiple decades, which indicates the interest in this flow field due to its widespread applicability for many various applications. I will highlight the works of Karper et al., which are the few experimental works which exist on this study. Many works, such as the Leiv et al. As well as Zhang et al., typically use Karper's work for validation of their numerical models, and I do the same throughout my work as well, and I will show this once we discuss the computational methodology. Shown here are the Reynolds-averaged Navier-Stokes equations, or the RANS equations, which govern the physics of the jet impingement heat transfer problem. These are the conservation of momentum, so the continuity equation, momentum equation, and the energy equations. To solve the mentioned equations, a computational study is carried out using the commercial computational fluid dynamic software StarCCM+. The computational model is considered as incompressible, three-dimensional, and to model the turbulent nature of the flow, the realizable K-epsilon model is used. And all Y plus wall treatment is also implemented here. Moreover, the fluid properties were considered temperature dependent. The disk being cooled was considered as steel, also with constant properties. Regarding the two modeling approaches, the moving reference frame simulation is considered steady, and the average Nusselt number was monitored after each iteration until no visible change in the Nusselt number was reported, indicating a converged solution is achieved. The unsteady moving mesh simulation employed a time step of around 1.6 milliseconds and a total simulation time of around 5 seconds, which eventually equates to around 8 whole revolutions. In terms of boundary conditions, a mass flow inlet is imposed at the inlet and is adjusted to match the desired jet Reynolds number. A constant inlet or jet temperature of around 310 Kelvin is considered, and a uniform heat flux of around 250 kilowatts per meter squared is applied to the bottom surface of the disk. This is to match some of the works of Karper et al. As well as Leiv et al. Finally, the fluid to solid interface is assigned a rotational speed of around 10.75 radians per second to achieve the desired rotational Reynolds number, and all fluid-solid interfaces have a no-slip boundary condition imposed. A hexahedral mesh topology is used to generate the mesh. In total, there are around 13 million cells. Refinement zones include the nozzle, the free jet region, as well as near the impingement surface. These regions are expected to have large velocity and or pressure gradients, which require a very fine mesh in order to capture. Therefore, the mesh was refined in these zones. Moving to the results now, we will first look at the average heat transfer along the disk, indicated by NU bar. The figure shown here shows the average Nusselt number with respect to the jet Reynolds number for different grid resolutions using the moving reference frame approach. The solution can be said to be grid independent as shown due to the less than 1% change from using 10 million cells compared to 13 million cells. Moreover, the moving reference frame and the moving mesh predict the average heat transfer within 10% of the correlation proposed in the work of Carper et al. It should also be noted here that in the work of Carper et al., a maximum error of around 34% was reported when comparing their correlation with experimental work. Moreover, as expected, like stationary jet impingement, we have an increase in the heat transfer performance with an increase in the jet Reynolds number. Moving to the local heat transfer characteristics, we can see the Nusselt number with respect to the radial location from the center of the disk at R by D is equal to 0 to the edge of the disk at R by D is equal to 10. Curves are shown for moving mesh and symbols indicate moving reference frame results. There is less than 1% variation between the MRF and the MM results, which indicates both approaches can be used fairly accurately for axisymmetric jet impingement heat transfer cases when cooling rotating surfaces. Like stationary impingement, there is a maximum in the Nusselt number within the stagnation region of the jet, which is at R by D is equal to 0. This is mainly due to the thinning of the boundary layer upon impingement. Beyond the stagnation region, there is a reduction in the Nusselt number towards the edge of the disk, where the Nusselt number is a minimum. For increasing jet Reynolds number, as previously mentioned, there should be an increase in the local Nusselt number, which is what we see. Finally, we can see from these results that near the stagnation region of the jet, heat transfer can be considered to be jet dominated, and towards the edge of the disk, where curves of constant jet Reynolds numbers merge, we can see that heat transfer tends to be more rotationally dominant. However, further studies need to be conducted at a wide range of rotational Reynolds numbers to understand the phenomena here. I would like to end this presentation by highlighting a major disadvantage to the moving reference frame approach. This is mainly under asymmetric conditions where the moving reference frame will tend to fail. Using moving reference frames, we can see the effective rotation. However, this effect is only seen for a specific geometrical position of the disk, whereas for moving mesh, since the mesh is physically rotating, we can see this cooling effect is more practical. This problem for moving reference frame can be solved by carrying out several moving reference frame simulations with the disk displaced at different angular positions. By superimposing all of these moving reference frame simulations, we can almost extract the exact same image we see from the moving mesh case. However, this is still only an approximation, and we cannot get the exact same solution as the moving mesh. To conclude, we looked at the average and local heat transfer characteristics for a submerged jet impinging a heated rotating disk. Higher heat transfer rates are achieved for increasing jet and increasing rotational Reynolds numbers. For moving reference frames and moving mesh techniques, the results are within roughly 1% of each other. However, this is only under axisymmetric impingement cases. The moving reference frame can be implemented with good accuracy while reducing computational cost, as opposed to using a moving mesh approach, which is far more computationally expensive. The heat transfer is also found to be rotationally dominant towards edge of the disk. However, the heat transfer tends to be more jet dominated within the stagnation region. Finally, multiple moving reference frame simulations with the jet nozzle angularly displaced can be used to approximate a moving mesh simulation. However, the accuracy of the moving reference frame for axisymmetric cases should still be addressed.